So this is our last section in Chapter 2, 210, term of a systematic account. So 210, term of a systematic account. Work. So by systematic account, we'll be talking about so savings account or some such thing where you make regular periodic deposits or systematic deposits. And we're going to need some formulas here. And again, by the term, we're going to talk about the present value of a systematic account, like how much you need to deposit each time to reach a certain goal. Okay, so we're going to need some formulas today. So as a quick review, we have the future value of a periodic deposit. These get a little bit messy sometimes, but that's all right. So B equals the payment. This P stands for payment, right? Since it's periodic, not principal so much. 1 plus R over N to the NT minus 1 all over R over N. And then we have a formula. And really this next formula comes from just solving this one for P, the payment amount. And this gives you the present value of a periodic deposit. Present value periodic deposit. In other words, this will give you the amount of monthly payment you need to make to reach a certain goal, or a B, a value of B for the balance that you want in the future. So when we solve that thing up there for P, we end up getting B times R over N all over 1 plus R over N to the NT minus 1. It can be a little tricky to, put in your calculator. Make sure you nest your parentheses and group things in the numerator and denominator. It'll be fine. Okay. Of course, we'll also probably need today the compound interest formula, which, by the way, is also the future value of a single deposit. So, future value of a single deposit. Also compound interest. That's the one we've been using for a while. The balance will equal the principal this time times 1 plus R over N to the NT. N, of course, is the number of compounding periods per year. Well, let's start out with example 1 over on page 130. Okay. I get this fellow named Jake, wants to deposit money into a savings account, pays 1.2% interest compounded monthly. Okay. And he is going to just make a single deposit. Okay. So we're not making periodic deposits yet. So okay, 1.2% interest monthly. They want us to write the general compound interest formula for this single deposit, okay? Using logarithms, right? Because remember, we use logarithms to solve for exponential functions. And what's up in the exponent most of the time with these? That's the t for time, the number of years, which is the term that we'll be looking for most of the time. All right, so we will have his balance will be his principal times 1 plus 0.012 over 12 to the 12t. Okay. And they want us to solve this thing for t. So to get that t out of the exponent, we're going to need to take some logarithms. I actually will prefer to write this, with the b over on the other side. you know my little hang-ups. Like the thing I'm solving for over on the left. Well, the first thing we have to do is clean it up, right? Let's divide both sides by p. And then we can also combine, this thing in the middle here. So if we divide both sides by p and combine what's inside the parentheses, we should get 1.001, I believe it is. Yep, 2 zeros. To the 12t equals b over p. Okay. And now that we've cleaned this up, we can go ahead and take the logarithm of both sides, and we'll do the version where we use the log of the same base. So the base of this exponential function here is 1.001. So one of our methods will use a log of that very same base on both sides. So you take the log base 1.001 of 1.001 to the 12t, and the same to the other side, 1.001 on the base of b over p. Well, on the left-hand side, that log undoes the exponential function, and we're just left with 12t equaling what we have over on the right-hand side, equals the log base 1.001 of b, no, make that fit right, b over p. And then, of course, we just divide both sides by 12. So we end up with t equals log base 1.001 of b over p, and that whole thing over 12. And they didn't want us to evaluate, any log. Well, we don't have a number inside the parentheses to do that. But that would be the general form. I think in the next example, they'll have us do it differently. Okay? So in the check for this one, they're going to have you do a similar thing. You're going to have Martina depositing $200 in account, 1% interest, compounded quarterly. So be careful with your end. Okay? He wants to write an expression for how long it will take her deposit to grow to 300. So I would ask you all right now to pause the video, go back and take a look at example 1. We're going to actually throw some numbers in here now, right? We found what t is. Okay, we'll probably have to go back in and work out whatever base this is. It'll be slightly different, but take a minute and see if you can run through this and figure out how long this will take in terms of the log. So don't evaluate the log. Hope you've had a minute to try this out. So let's set it up here. We're using the future value of a single deposit again. So $200 times 1 plus 0.01 divided by 4 this time, compounded quarterly, to the 4t needs to equal $300 at some point in the future. We want to kind of find out when that will be. We got to divide both sides by 200, and 1.01 divided by 4 ends up being 1.0025. The 4t, and 300 divided by 200 just reduces to 3 halves. Divide top and bottom by 100. Skip that step. And now let's take the log of both sides with the base 1.0025. So the log base 1.0025 of 1.0025 to the 4t equals the log 1.0025 of 3 halves. Of course, again, on the left-hand side, the log of the same base undoes the exponential function with that base. So we end up with 4t equaling log 1.0025 of 3 halves And then all we need to do is divide both sides by 4. So t equals log 1 point, that look more like a subscript, 1.0025 of 3/2 all over 4. And that's where they asked us to stop and not evaluate it with a log. We could put that in our calculator and figure out how many years it will take to happen. My guess is that interest rate of 1% is going to take a while. So you might want to find an alternate investment. All right, so now in example 2, I believe they're going to have us work through the problem in example 1 using the other method of logarithm solving that we learned. But let's review really quickly though. What we'll be using is the log power property. Log power property. And that just says if I have log base whatever, base b of a to the c power, that exponent can come out front. We can rewrite it as c times log base b of a. Or same with natural log, right? If we had natural log, which is the log base e of a to the c power, same thing. We can pull the c out front. Okay, so we'll use this property to solve the same problem in a slightly different way. So let's take a look at example 2. That's over on page 132. It says use property logarithm to solve example 1 the different way. So if these properties yield the same result as method in Jake's situation. So probably what we should do is go back to example 1 and work out how many years that will actually take. The only way to compare them directly, and we'll do the same for this one. So if we go to example 1 and put this in our calculator, well, this part's a little confusing in the book, the way they set that up. They're assuming that we're going to use for a balance, I'm just doing a different color. We're going to plug in a balance of 1,000, I believe, that we want. All right, and the initial deposit, the principal is 800, right? And they want to know when that 1,000 actually grows, or that 800 actually grows to 1,000. So let's just plug this in real quick. So we'd end up with t equals log 1.001 of, yeah, do that, 1,000 over 800, and we'll just plug that in directly to our calculator here. So let's see, control log 1.001 1,000 divided by 800. Now we get 223.26. That's not years, remember, because we're compounded how often? We're compounded 12 times per year, so that's actually the number of months. So 223.26 months and we're probably more interested in how many years, so we'll just divide that by 12. So take that result, I think we can just hit divided by 12. And we get 18.6 years for this to happen. These interest rates are very, very low. It took 18, almost 19 years to acquire $200, so it's a little bit goofy. But let's see if we also get 18.6 years solving it the other way in example 2. So in example 1, we're going to use, like we did over there, b equals 1,000 and p equaling 800. Okay, so let's set this up here. So let's plug it back into the formula right from the get-go. So we would have 800 times 1 plus 0.012 over 12 to the 12t, needing to equal 1,000. Right, so when we clean that up, we divide both sides by 800. Again, we get the 1,001 to the 12t, and 1,000 divided by 800 works out to 1.25. So now we can, instead of taking the log of base 1.001, maybe you have a calculator that only does base 10 or natural log. So let's just take the log base 10 of both sides. Log base, we don't have to write the 10, of 1.001 to the 12t is the log base 10 of 1.25. And we use our product property. Bring that exponent of 12t out to the front and rewrite it. So 12t times log 0.001 equals log 1.25. And then we can divide both sides by 12 log 1.001. So we end up with t equals log base 10 of 1.25 divided by 12 times log 1.001. We'll do the equals approximately. So we'll go, make sure, you know, when you put this in your calculator, you parenthesize that and group it. Okay. So let's put that in. So we'll have log, leave that blank. If they leave it blank, they assume base 10. So 1.25, outside the parentheses, divided by, so here's where I want to group it, right? I want to do 12 times log 1.001. That will get it. And again, so we get 18.6 years again, using either method. So it'll be okay. Maybe you're wondering why this one came out directly in years when the other one came out in months, and then we had to divide it by 12. But if you remember, in this last step, when we were solving for t, we did divide here by 12. So the result is in years directly, right? Because the division by 12 is kind of baked in there. All right, the check is just kind of a random log problem to solve. So we'll check, for example, 2, using that 1-to-1 property, power property. So 3.6 equals 1.5 for 5t. Of course, you know I like to change things a little bit. So we're going to call it 1.5 to the 5t power equals 3.6. So using the same method we just did, pause the video, take a moment, see if you can solve this for t, and I'll be right back with you. All right, so hopefully you've worked through this, and you've got t equals 0.6 years. I'm assuming it's in years. If you didn't get that, let's go through it. We don't have to clean anything up. We have pure exponential function on the left. Okay, so let's just take the log base 10 of both sides. And by the way, you could also take the natural log of both sides as well. Let's go ahead and do that. Let's take the natural log just for something different, right? So let's try the natural log, see if this works out, of 1.5 to the 5t will equal the natural log of 3.6. Okay, not to confuse you, but we can use a log of any base, right, and use the exponent property and get the answer we need. So again, the exponent comes out to the front, 5t times natural log of 1.5 equal the natural log of 3.6. we just divide both sides by 5 natural log of 1.5. Natural log of 3.6 divided by 5 natural log of 1.5. And let's go to our calculator. So natural log, so here to the left of regular log. So the natural log of 3.6 divided by, whoops, go back in, outside of there, divided by, it's going to be 5 times natural log of 1.5. See if this gets us. So about 0.6 years. And you would have gotten the same. Let's do a regular log. Let's try control log base 10 of 3.6 divided by, parentheses, 5 times log base 10, whoops, of 1.5. Should come out the same if I entered it right. Still 0.6, so either log. So it equals approximately 0.6 years. Again, I'm assuming they were in years. I didn't really say. Okay, let's move on to example 3. It gets a little bit more complicated. We're over on page 133 in your book. So example 3. So read this over to Gary Nam, want to make monthly deposits. So now we're not doing single deposit, we're doing the periodic deposit. Okay, to a savings account, 1.95% compounded monthly. I want to know how long it'll take for it to reach $10,000. So we are going to need our formula for the future value, randomly green, again, what's going on there, future value of a periodic deposit, right, and that's the B equals monthly payment, or periodic payment, of 1 plus R over N to the NT minus 1. That whole thing over R over N. So this one could get a little bit messier. Okay? So they're going to be depositing $400 every month, and they want it to equal $10,000. So let's plug in the variables that we have here. Again, I'm going to move the capital B off to the right, as you know I do. So the P is $400 times 1, double up our parentheses, plus the rate is 0.0195, compounded monthly, 12, to the 12T minus 1, all over 0.0195 over 12. And we need that to end up equaling $10,000. And we want to know when, how long it will take. So we'll have to solve for T. We have some cleaning up to do here. Let's probably will be better if we simplify some of our things in parentheses and in the denominator there. So let's do that. So we end up with 400, right, times, well, it's going to be 1.0195 over 12. Ends up being 1.001625, okay, to the 12T minus 1 all over, and we know again that 0.0195 over 12 is 0.001625. Okay, needs to equal again 10,000. Well, we don't have a purely exponential function, so we are going to have to clean this up. So we'll have to divide by 400 and also multiply by 0.001625. We could do that both at the same time, right? By really just multiplying both sides by the reciprocal. So if I do this, multiply by 0.01625 over 400, and I've got to do the same to the other side, times 0.01625 over 400. Okay, of course over here these guys will cancel. That happened. All right, and then the 400s cancel. Okay, so that will leave us with 1.001625 to the 12t minus 1, equaling 10,000 times that mess over there is going to give us 0.040625, 0.040625. We put that in our calculator. Well, we're not quite cleaned up yet. Looks like we should probably add 1 to both sides. All right, so we end up with 1.001625 to the 12t will equal, when we add 1.040625. Okay. But now we can just take the log of both sides. Did they give us a specific method? And I guess they go through both methods. We'll use the one where we just take the log base 10 of both sides. So log base 10 of 1.001625 to the 12t will be the log base 10 of 1.040625. I guess technically I don't need parentheses there. All right, let's bring the exponent out front. So 12 times log of 1.001625 will equal the log 1.040625. Oh, forgot the t, 12t. So now let's divide both sides by 12, log 1.001625, right? So we'd have t will equal log 1.040625 divided by 12 times log 1.001625. And we can go carefully put this into our calculator, and it'll tell us how long it will take. Okay, so let's do control log, and let me go back. That was 1.040625. 1.040625. Make sure I got that right. 5. Okay. Outside the parentheses, divided by this 12 times log of 1.00165. 1.00165. Let's see. It's like 2.04 years. Double check my numbers here. 1.0265. Okay. So 2.04 years it will take for your monthly deposits of $400 to reach the balance required of $10,000. Okay. Well, hopefully you're kind of getting the hang of this. So let's have you guys try the check. Okay. Again, we'll be using future value of a periodic deposit. Using this, remember P is the amount of monthly periodic deposits. 1 plus R over N, the NT minus 1, all over R over N. Okay, so read that over, plug in what needs to be plugged in, and let's see how we do. I'll be back with you in a moment. All right, well, hopefully you've got an answer of 2.06 years. So let's see how we go about that. So she's depositing $200 a month at a rate of 1.26%, and she wants it to reach a balance of $5,000. Okay? So let's run through this then. Extend that page down. So $200 a month, so our P is 200. So we need 200. Yep, okay. Wasn't sure if I was recording or not. So we need 200 times 1 plus, our rate was 0.0126 over 12 to the 12t. That's 1. This whole thing over 0.0126 over 12 needs to equal $5,000. Okay, we'll start simplifying and cleaning it up. So we'll have 200 times, this will end up being 1.00105, I believe, to the 12t minus 1, all over 0.00105 when we divide those out in the numerator, equaling 5,000. So let's multiply both sides by the reciprocal here. So 0.00105 over 200 times this side. And this side times the same thing. So these guys will cancel, those guys will cancel. And we end up with 1.00105 to the 12t minus 1. And when we put that mess in the calculator over there, we should get 0.02625. And now let's just take the log base 10 of both sides. We could do the log base 1.00105, but whatever. So if we do log 1.00105 to the 12t, we'll get log of 0.02625. Bring the exponent out front. Divide both sides by 12 log mess, so we get t equals log 0.02625 over 12 times log 1.00105. All right, make sure we got the numbers correct there. So let's put that in our calculator. Control log over of, what was it? I'm trying to remember all these numbers. 0.02625, 0.02625, divided by parentheses 12 times log of, oops, daisy, 1.00105, 1.00105. Okay, so we get -2. Yeah, well, okay, something didn't quite go right here. Hang on one second. Oh, you know what we didn't do? We didn't go back and add the 1 on both sides. Aha. That's what we forgot to do. We actually dropped, let me go back here to this step here. Right? So we kind of need to fix it from here on. Yeah, well, let's see here. So if we eliminate this stuff here, let's add 1. So that one little mistake really did kind of cost us quite a bit of error. So let's make sure we get this right. So our 1.00105 to the 12t, we have to add 1. We get 1.02625. There we go. Now let's take the log of both sides. Log of 1.00105 to 12t equals log 1.02625. Bring the exponent out front. Now we'll divide t. Let's drop that. Both sides out. So we get t equals log 1.02625 over 12. That's log 1.00105. Now let's see if we get a more reasonable answer. I think we can just kind of go up here. Having to type that again. I think that was our only change, isn't it? Should make it right. Okay, there we go. So 2.06 years. 2.06 years. Right. Every now and then, it's easy to make a simple mistake. If you get something that seems really unreasonable for a final answer, go back and take a look at what you might have done, kind of error you made. In this case, I forgot to add 1 to both sides up there. So, okay, we are in this section not going to do the part with systematic withdrawal accounts. It's not a common thing. It's not really worth our time right now. So, okay, well, that wraps up chapter 2.